Introduction to software engineering. Software engineering is a systematic, disciplined, quantifiable approach to the development, operation, and maintenance of software. It encompasses a wide range of activities, from understanding user needs to designing, building, testing, and deploying robust software solutions. This field applies engineering principles to software creation, ensuring reliability, efficiency, and maintainability. It addresses the challenges of developing complex software systems within budget and schedule constraints. Effective software engineering practices are crucial for delivering high-quality products that meet user expectations. The discipline continuously evolves with new technologies and methodologies. Understanding its core tenets is fundamental for any aspiring software professional. The primary goal of software engineering is to produce high-quality software that is reliable, efficient, and maintainable. This involves managing complexity, ensuring scalability, and adapting to changing requirements throughout the software's lifecycle. Software engineers leverage various tools, techniques, and processes to achieve these objectives. They often work in teams, collaborating to solve intricate problems and deliver innovative solutions. The emphasis is on creating software that not only functions correctly, but also provides a positive user experience. This systematic approach differentiates software engineering from mere coding, focusing on long-term sustainability and quality. Software Development Lifecycle, SDLC. The Software Development Lifecycle, SDLC, is a structured process that outlines the stages involved in developing a software application. It provides a framework for managing the entire project, from initial concept to final deployment and ongoing maintenance. The SDLC ensures that all critical aspects of software development are addressed systematically. This structured approach helps teams deliver high-quality software efficiently and effectively. It typically includes phases like planning, analysis, design, implementation, testing, and maintenance. Adhering to an SDLC model helps minimize risks and improve project predictability. Different models exist, each suited for various project types and organizational needs. SDLC Phase 1. Requirements Gathering. Requirements gathering is the crucial initial phase of the SDLC, focusing on understanding and documenting what the software needs to achieve. This involves extensive communication with stakeholders to identify their needs, expectations, and constraints. Techniques like interviews, surveys, workshops, and prototyping are commonly employed to elicit comprehensive requirements. Clear and unambiguous requirements are vital for the success of any software project. Poorly defined requirements often lead to project delays, cost overruns, and ultimately, user dissatisfaction. This phase lays the foundation for all subsequent development activities, ensuring the final product aligns with business objectives. Documenting these requirements meticulously is essential for future reference and validation. SDLC Phase 2. Design Principles. The design phase translates the gathered requirements into a detailed blueprint for the software system. This involves defining the system's architecture, components, interfaces, and data structures. Key design principles, such as modularity, cohesion, and coupling, are applied to create a robust and maintainable system. Modularity ensures that the system is broken down into smaller, manageable parts. Cohesion refers to the degree to which elements within a module belong together, while coupling describes the degree of interdependence between modules. Good design minimizes complexity and facilitates future enhancements. This phase often results in architectural diagrams, database schemas, and user interface mockups. A well-designed system is easier to implement, test, and maintain over its lifespan. SDLC Phase 3. Implementation and Coding. The implementation and coding phase is where the software design is transformed into actual executable code. Developers write code using chosen programming languages, adhering to coding standards and best practices. This phase requires meticulous attention to detail, logical thinking, and problem-solving skills. Developers often work in integrated development environments, IDEs that provide tools for writing, debugging, and testing code. The goal is to produce clean, efficient, and well-documented code that accurately reflects the design specifications. Regular code reviews are often conducted to ensure quality and consistency. This stage is highly iterative, with developers continuously refining and optimizing their code. Successful implementation directly impacts the software's performance and stability. SDLC Phase 4 – Software Testing. Software testing is a critical phase designed to identify and fix defects, ensuring the software meets its specified requirements and quality standards. This involves executing the software under various conditions and comparing actual results with expected outcomes. Different types of testing are conducted, including unit testing, integration testing, system testing, and acceptance testing. Unit testing verifies individual components, while integration testing checks interactions between modules. System testing evaluates the complete system, and acceptance testing confirms user requirements are met. Thorough testing helps prevent costly errors in production and enhances user confidence. Automated testing tools are frequently used to improve efficiency and coverage. This systematic validation process is indispensable for delivering reliable software. SDLC Phase 5 – Deployment and Maintenance. The deployment phase involves making the software available to end users. This includes activities such as installation, configuration, and release management. Careful planning is essential to ensure a smooth and seamless transition from development to production environments. Once deployed, the software enters the maintenance phase, which is an ongoing process of monitoring, updating, and enhancing the system. Maintenance activities include fixing bugs, improving performance, adapting to new environments, and adding new features based on user feedback. This phase is crucial for the long-term viability and success of the software. Effective maintenance ensures the software remains relevant, secure, and functional over time. It represents a significant portion of the total cost of ownership for any software product. Agile Methodologies Overview. Agile methodologies represent a set of principles for software development that emphasize iterative development, collaboration, and flexibility. Unlike traditional waterfall models, Agile focuses on delivering working software frequently, typically in short cycles called sprints or iterations. This approach allows teams to adapt quickly to changing requirements and incorporate feedback throughout the development process. Key tenets of Agile include customer collaboration, responding to change over following a plan, and individuals and interactions over processes and tools. The Agile Manifesto, published in 2001, formalized these values. Agile promotes a culture of continuous improvement and transparency. It has become a dominant approach in modern software development due to its effectiveness in complex and dynamic projects. Scrum Framework in detail. Scrum is one of the most popular Agile frameworks, designed for managing complex software and product development. It is an iterative and incremental approach that organizes work into short, fixed-length iterations called sprints, typically lasting 1 to 4 weeks. Each sprint aims to deliver a potentially shippable increment of working software. Scrum defines specific roles: the product owner, who manages the product backlog, the Scrum Master, who facilitates the process and removes impediments, and the development team, responsible for building the increment. Key events include sprint planning, daily Scrum meetings, sprint review, and sprint retrospective. These elements work together to promote transparency, inspection, and adaptation. Scrum's simplicity and effectiveness make it widely adopted across industries. Kanban for software development. Kanban is another popular Agile methodology that focuses on visualizing work, limiting work in progress, WIP, and maximizing efficiency. It originated from the Toyota production system and is highly effective for continuous delivery and flow-based development. The core of Kanban is the Kanban board, which visually represents workflow stages using columns and tasks as cards. Teams pull tasks from one stage to the next as capacity allows, rather than pushing work through. Limiting WIP helps identify bottlenecks and improve throughput. Kanban is highly adaptable and can be applied to various contexts, from software development to IT operations. Its emphasis on continuous improvement and evolutionary change makes it a flexible choice for many teams, Kanban helps optimize the flow of value to customers. Version Control Systems, VCS. Version Control Systems, VCS, also known as Source Code Management, SCM systems, are essential tools for tracking changes to files and coordinating work among multiple people. They maintain a complete history of every modification made to the codebase, allowing developers to revert to previous versions, compare changes, and merge contributions seamlessly. VCS prevents conflicts when multiple developers work on the same files simultaneously. It provides a safety net, ensuring that no work is lost and that changes can be easily tracked and undone. Centralized VCS, like SCM, and distributed VCS, like Git, are the two main types. Modern software development relies heavily on VCS for collaboration and project integrity. Understanding VCS is fundamental for any software engineer. Git, Distributed Version Control. Git is a widely used distributed version control system, DVCS, that allows developers to track changes in source code during software development. Unlike centralized systems, every developer's working copy of the code is also a full-fledged repository with its own history and version tracking capabilities. This distributed nature offers significant advantages, including offline work, faster operations, and enhanced resilience. Git enables seamless collaboration through features like branching and merging, allowing developers to work on separate features concurrently without interfering with the main codebase. Commands like git clone, git commit, git push, and git pull are fundamental to its operation. GitHub, GitLab, and Bitbucket are popular platforms built around Git. Mastering Git is an essential skill for modern software engineers. Object-Oriented Programming, OOP concepts. Object-Oriented Programming, OOP, is a programming paradigm based on the concept of objects, which can contain data and code. The primary goal of OOP is to increase the flexibility and maintainability of large software systems. Key OOP principles include encapsulation, inheritance, polymorphism, and abstraction. Encapsulation bundles data and methods that operate on the data within a single unit. Hiding internal implementation details. Inheritance allows new classes to inherit properties and behaviors from existing classes, promoting code reuse. Polymorphism enables objects of different classes to be treated as objects of a common type. Abstraction focuses on showing only essential information and hiding complex implementation. These principles help in creating modular, reusable, and scalable code. Languages like Java, Python, C++, and C# are popular OOP languages. Data structures and algorithms. Data structures are specialized ways of organizing and storing data in a computer so that it can be accessed and modified efficiently. Common data structures include arrays, linked lists, stacks, queues, trees, and graphs. Each structure has its strengths and weaknesses, making it suitable for different types of problems. Algorithms are a set of well-defined instructions or a step-by-step procedure to solve a specific problem or perform a computation. Examples include sorting algorithms like quicksort, merge sort, and searching algorithms like binary search. The choice of appropriate data structures and algorithms significantly impacts the performance and scalability of software. Mastering these concepts is crucial for writing efficient and optimized code. They form the bedrock of computer science and software engineering. Database Management Systems, DBMS. A database management system, DBMS, is software that allows users to define, create, maintain, and control access to a database. It acts as an interface between the database and its end users or application programs, ensuring data consistency, integrity, and security. DBMS provides tools for data storage, retrieval, and manipulation. It handles complex operations like concurrency control, backup, and recovery, which are essential for multi-user environments. Relational Database Management Systems, RDBMS, are the most common type, organizing data into tables with rows and columns. Other types include NoSQL databases, which offer different data models. A robust DBMS is critical for applications that handle large volumes of data, ensuring efficient and reliable data management. Understanding DBMS is vital for designing and building data-driven applications. SQL and NoSQL databases. SQL, Structured Query Language Databases, primarily RDBMS, organize data into tables with predefined schemas. They enforce strict data integrity rules and are excellent for complex queries and transactional applications where data consistency is paramount. Examples include MySQL, PostgreSQL, Oracle, and SQL Server. NoSQL, not only SQL databases, on the other hand, offer more flexible schema designs and are better suited for handling large volumes of unstructured or semi-structured data. They prioritize scalability and availability over strict consistency, often used in big data and real-time web applications. Common NoSQL types include document databases, MongoDB, key-value stores, Redis, column family stores, Cassandra, and graph databases, Neo4j. The choice between SQL and NoSQL depends on the specific application requirements, data model, and scalability needs. Each type offers distinct advantages for different use cases. Web development fundamentals. Web development involves building and maintaining websites and web applications that run over the internet. It encompasses a broad range of tasks, including web design, web content development, client-side scripting, server-side scripting, and network security configuration. The internet's pervasive nature makes web development a highly in-demand skill. Fundamental concepts include understanding how the internet works, client-server architecture, and the role of various protocols like HTTP, HTTPS. A basic understanding of front-end and back-end technologies is essential. Modern web development emphasizes responsive design, performance optimization, and security. It is a continuously evolving field, requiring developers to stay updated with new technologies and frameworks. Building interactive and user-friendly web experiences is the core objective. Front-end development essentials. Front-end development focuses on the user-facing side of a website or web application, often referred to as the client side. It involves creating everything that users see and interact with directly in their web browsers. The three core technologies for front-end development are HTML, CSS, and JavaScript. HTML, hypertext markup language, structures the content. CSS, cascading style sheets, styles the appearance. And JavaScript adds interactivity and dynamic behavior. Modern front-end development also heavily utilizes frameworks and libraries like React, Angular, and Vue.js to build complex user interfaces efficiently. Responsive design is paramount, ensuring websites look and function well across various devices and screen sizes. A strong understanding of user experience UX and user interface UI principles is also crucial for effective front-end development. Back-end development essentials. Back-end development, also known as server-side development, focuses on the logic, databases, servers, and APIs that power a web application. It handles the behind-the-scenes functionality that users don't directly see, but is essential for the application to work. Back-end developers write code that communicates with databases, processes user requests, authenticates users, and manages server operations. Popular back-end programming languages include Python, Java, Node.js, JavaScript, Ruby, PHP, and C#. Frameworks like Django, Spring, Express.js, and Ruby on Rails accelerate development. Understanding database interactions, server management, and API design is critical. The back-end ensures data security, performance, and scalability, forming the robust foundation upon which the front-end operates. It is the invisible engine driving the web experience. API design and RESTful services. An application programming interface, API, defines a set of rules and protocols for building and interacting with software applications. It allows different software systems to communicate with each other, enabling seamless data exchange and functionality sharing. REST, representational state transfer, is an architectural style for designing networked applications, widely adopted for web APIs. RESTful APIs use standard HTTP methods GET, POST, PUT, DELETE to perform operations on resources, which are identified by unique URLs. Key principles of REST include statelessness, client-server separation, and a uniform interface. Good API design emphasizes clarity, consistency, and ease of use for developers. It is crucial for building scalable and interoperable systems. Understanding API design is fundamental for modern software integration and microservices architectures. Software architecture patterns. Software architecture patterns are generalized, reusable solutions to common problems in software design. They provide a blueprint for structuring software systems, guiding decisions about components, their relationships, and how they interact. Examples include the layered architecture, client-server, microservices, and event-driven architecture. Layered architecture separates concerns into distinct layers, like presentation, business logic, and data access. Client-server defines two types of hosts, a client requesting resources and a server providing them. Microservices break down an application into small, independent services, each running in its own process. Event-driven architecture facilitates communication through events. Choosing the right architectural pattern is crucial for a system's scalability, maintainability, and performance. These patterns help manage complexity and ensure long-term viability. Cloud computing in software engineering. Cloud computing involves delivering on-demand computing services, including servers, storage, databases, networking, software, analytics, and intelligence, over the internet, the cloud. It offers significant benefits for software engineering, such as scalability, flexibility, and cost-effectiveness. Cloud platforms like AWS, Azure, and Google Cloud provide infrastructure, IaaS, platforms, PaaS, and software, SaaS, as services. This allows developers to focus on building applications rather than managing underlying infrastructure. Cloud-native development leverages cloud services to build and run scalable applications in dynamic environments. Understanding cloud concepts, deployment models, and service offerings is increasingly vital for modern software engineers. It enables rapid deployment, global reach, and efficient resource utilization. The cloud has fundamentally transformed how software is developed and delivered. DevOps principles and practices. DevOps is a set of practices that combine software development, dev, and IT operations, ops, to shorten the system's development lifecycle and provide continuous delivery with high software quality. It aims to bridge the gap between development and operations teams, fostering collaboration and communication. Key principles include automation, continuous integration, CI, continuous delivery, CD, and continuous monitoring. CI involves frequently merging code changes into a central repository, followed by automated builds and tests. CD extends CI by automatically deploying all code changes to a testing or production environment. Continuous monitoring ensures application performance and health are constantly tracked. DevOps culture emphasizes shared responsibility and feedback loops. It significantly improves release frequency, time to market, and system reliability. Implementing DevOps practices is crucial for modern agile software delivery. Security in software development. Software security is paramount in today's digital landscape, focusing on protecting software and data from malicious attacks and unauthorized access. It involves designing, developing, and testing software to minimize vulnerabilities and ensure resilience against threats. Security must be integrated throughout the entire SDLC, from requirements gathering to deployment, rather than being an afterthought. Common security practices include secure coding guidelines, input validation, authentication and authorization mechanisms, and encryption. Identifying and mitigating common vulnerabilities like SQL injection, cross-site scripting, XSS, and broken authentication is critical. Regular security audits, penetration testing, and vulnerability assessments help identify weaknesses. A proactive approach to security, often called security by design, is essential for building trustworthy software. Neglecting security can lead to severe financial, reputational, and legal consequences. Software Quality Assurance, SQA. Software Quality Assurance, SQA, is a systematic process that ensures software products meet specified quality standards and requirements. It encompasses a set of activities designed to guarantee quality throughout the entire software development lifecycle, not just during the testing phase. SQA involves defining quality metrics, establishing quality processes, conducting reviews and audits, and implementing continuous improvement strategies. The goal is to prevent defects rather than just detecting them. SQA activities include process definition, quality planning, quality control, and quality improvement. It ensures adherence to standards, methodologies, and procedures. By integrating quality checks at every stage, SQA helps deliver reliable, efficient, and user-friendly software. A robust SQA program is vital for an organization's reputation and customer satisfaction. It is a continuous effort to enhance the overall quality of software products. Future trends in software engineering. The field of software engineering is constantly evolving, driven by technological advancements and changing user demands. Several key trends are shaping its future. Artificial intelligence, AI, and machine learning, ML, are increasingly integrated into software, enabling intelligent features and automation. Serverless computing allows developers to build and run applications without managing servers, further simplifying deployment. Edge computing brings computation closer to data sources, reducing latency. Low-code, no-code platforms are empowering non-developers to create applications, accelerating development cycles. Quantum computing, while nascent, holds the promise of solving complex problems currently intractable. Ethical AI, data privacy, and sustainable software development are also growing concerns. Staying abreast of these trends is crucial for software engineers to remain relevant and innovative. The future promises even more sophisticated and interconnected software systems.